welcome back from lunch, everyone. Welcome to my amazing talk about running QEMU in UEFI. So first about me, if you haven't seen me or heard of me or know me, I'm at Graf. I've done things like the PowerPC, server PowerPC, KVM port, or was an active maintainer for QEMU there as well. I did the nested SVM implementation. I've spent a lot of the last couple of years trying to push SUSE to pursue the ARM server market, which we're finally entering, or have entered, so it's basically done. As part of that, one thing I did was U-boot UEFI support, so you can run UEFI binaries inside of U-boot so that your embedded environment starts to look more like something that you actually want to run on. That's a completely different story. It just means that because of that, I had a rough idea on how UEFI works, and this presentation is going to show you some of that as well. So the initial problem that we faced was about half a year ago. I was at Linaro Connect and at one of those enterprise steering committee meetings, and one of those member companies said, well, if you buy an ARM server and you plug in a PCI card into that PCI card does not work properly on boot up, because what happens is that if you take the PCI card on an x86 system, you will actually see that getting used by firmware. So in this case, it actually shows you something on the screen if it's a graphics card. But on an ARM server, you just don't see anything. That PCI card basically is unsupported by firmware. And the reason that is that the ROM that contains the driver for that card is on the card itself. So PCI cards have a small ROM in it, or flash ROM these days, that contains a driver, usually a UEFI driver these days, to actually leverage that adapter from the firmware. But because it's x86 code, we can't just run it on ARM, can we? So let's take a look at what the difference really is between this ARM and this x86 thing. So every time I talk about ARM or x86 in this context, I only talk about 64-bit variants. I don't talk about 32-bit ones because they're odd and different. But the 64-bit variants, basically one of the big differences between different architectures is the register set. So on ARM, you have about 32 different registers. It's more like 31 to 30. But you have a lot of registers there. On x86, you have different registers that are named differently, that have sometimes special semantics attached to them, and obviously a much smaller number than on AH64, on ARM. You don't need to actually remember all the details there, but keep in mind that this is one major difference. So what if we want to move some values from a register to another register? On ARM, we just want to move something from register 0 to register 1, and on x86 from register RX to BX, or A to B, really, in 64-bit width. What you do is you usually issue an instruction to the CPU to say, CPU, please move data from this register to the other register. And while the assembly of that looks pretty similar between the different architectures, that's really just a human-readable form of what the CPU reads. The CPU reads opcodes, which are these hex values down there. And you can probably tell at a glimpse already that they're pretty incompatible. Right? Running one of them on the other just simply doesn't work. And making one of them work on the other, that's exactly what QEMU does. I mean, I'm pretty sure that almost everybody of you guys knows that, but I want to make sure we're on the same page. So what is QEMU? QEMU gives you, has different modes of emulation. The usual mode of emulation that most people here are familiar with, because we had KVM forum, is full system emulation. In full system emulation, what you have is you have a machine, a full system. And QEMU is responsible for emulating every single part of that whole system. So it emulates hardware, the operating system, and your applications running inside. So every single part of that whole stack is emulated and is completely handled and translated by QEMU. And if you do KVM, you basically just take a small piece, which is the CPU down here, and just plummet that through to actual hardware. But the concept is still the same. You basically have this envelope of QEMU around everything. The second mode it has, which is lesser known, is Linux user. So in Linux user mode, what you have is QEMU only emulates the application layer and uses the boundary between application and the kernel as a boundary where it can hook itself into and then basically convert data structures from one to the other, from one architecture to the other, basically, from the semantic of one architecture to the other, to have an application for ARM, for example, run on an x86 Linux kernel. But UEFI is your firmware, right? And what your firmware does is essentially the same thing a kernel does. And has anybody ever seen applications running on UEFI with an actual boundary down there? No, right? There's no boundary. We'll get to that. So what is UEFI? So UEFI, if you have a system, normal PC, anything you buy these days that roughly looks like a server and doesn't come from IBM, you will want to, well, you want to have that on your IBM too, you just don't have the UEFI part in it. You want to be able to access devices to boot from. For example, you want to boot from your disk, you want to boot from, well, that's supposed to be a network card, even though it has graphics connectors. You want to be able to access the network, you want to be able to access the CD-ROM drive, you want to be able to boot, right? You obviously also want to be able to display things. So each of those pieces has a driver attached to them. And all of these drivers basically talk to the UEFI driver core and are able to communicate to each other randomly. So any random driver can talk to any other random driver inside of UEFI, and everything runs in a single address space. The way you can then run applications is that things like grub get loaded from the disk, and then grub establishes a communication channel to a driver to then reload more data from a disk to then interpret that, and for example, load Linux, boot Linux, and Linux throws away all of that stuff and establishes its own special runtime communication channel. That's just UEFI in a nutshell, 2-minute walkthrough. Now, let's dive into what UEFI actually does under the hood. So this driver, what does this driver do when you load up a driver, when the system initializes at first? The driver goes in and registers itself with that UEFI core. So it just calls a function on a callback pointer, which is the pattern throughout all of UEFI. Everything's an indirect function call. You call that function to register, look, I'm a new driver, I'm new in the system. And that thing really just only gets a struct, which then again has lots of fields. Some of them are function pointers, some of them are data structures with arbitrary data. So in this case, you just say, well, this driver just says, I'm a new driver, and I can either tell you whether I'm supported on a special new device, or I can start or I can stop on it. So that when then another driver core inside the system, like the PCIe driver core, for example, goes and finds a new PCIe device, it can instantiate a new PCIe object, which then again can probe all drivers in the system to see whether they are actually compatible with that new card, and if they are, instantiate that driver on top of that object. Make sense? All right. One thing you see here is that everything really is governed by that's the right point. Everything really is governed by the structure and function pointers going left and right and pointers getting passed everywhere. It's all a single address space. You don't have syscalls, you don't have anything of the likes. Later on, the starting happens on the driver. Later on, when the driver is then properly installed and you want to read data, all you need to do is from your GUP application, basically get the callback to that device. That wasn't one animation too much. Get the callback structure from the device and just call that read function to read from that device. So what happens if we now have all of this driver be of a different architecture? So imagine we want to emulate that driver, which means that driver is now running, say, x86, and everything around us is running ARM. How does that even work? So there are a few obstacles we need to come across. And just thought experiments we have to go through to figure out, is this feasible or not? So the most obvious one is do the data structures even look the same? Right? Do I have the same endianness? Do I have the same data structures? So this structure in memory is roughly looks like this. The pointers are just something I thought of, but roughly this is the way that structure looks like in memory. And one of the nice convenient parts in UEFI in a 64-bit world is that they look the same across different architectures as long as they have the same endianness, which we guaranteed because UEFI dictates that everything needs to be little endian. So the only case that wouldn't work is completely governed out, and our ARM and x86 systems actually have the exact same layout for all the data structures. So even sharing data structures between ARM and x86 would work, right? Unless you configured for big endian? Oh, sure, if you do big endian, you basically lost all of UEFI anyways. But you just do that after EFI is gone. The only thing that people might remember is padding, right? So padding is something that when you have data elements in your structure, fields that are not aligned at the same position. So for example, a pointer in a 64-bit world wants to be 64-bit aligned so that you can have an aligned data read from memory. Which means that usually what happens is that in the ABI it's defined that you have a certain padding, couple of certain padding bytes in your in between that 32-bit value and a 64-bit value, because otherwise the 64-bit value would not start at a 64-bit boundary. Fortunately enough, that actually applies to both architectures the same again. So all those 64-bit architectures essentially follow roughly the same ABI semantics for data layout. And that means we actually can share data between an x86 piece of code and an ARM piece of code. So, however, you remember all of these data structures we had, right? So imagine we now have some code, say an ARM Graf, that wants to call into an x86 read function that it receives from a struct that we really don't want to be able to interpret from the emulator part of view. So somehow we need to be able to trap that this ARM code is now trying to run x86 code. You could obviously marshal everything, but then we would have lots of lines of code, I don't know how many hundreds of thousands of lines of code for different protocols to basically just marshal that struct into function pointers that call the emulator that then call again the real function. So it's essentially unfeasible. But, oh yeah, we want to call that function. But what does a function call actually do? A function call basically just means the code that we write takes all of the parameters we have and puts them into individual registers. They are defined in the ABI which registers they are. So these are the ones for ARM. It then potentially also puts spillover registers on the stack. In this case, it doesn't. And then modifies the position counter to be the position counter of the function we want to call. So that it basically the next instruction that gets executed is the one from is the one we want to execute. There's more to it, but this is in a nutshell what happens. However, if we want to call x86 code, we have a real issue, because if we now just jump into that x86 code, we will execute things that on ARM will have different semantics and do different things because the instruction sets don't look the same. So we somehow need to get into QEMU. And how do we do that? There's a really, really nifty feature in modern CPUs, which basically every 64-bit CPU is, and that's called NORExecute. So NoExecute is a feature where you can say, well, I have these regions of memory that are mapped to do something. Usually you map them just as I can read to them, I can write to them, I can execute them. But you can also, using a special bit in the page table, say, well, this region on here, don't allow executing on it. Just allow reading and writing to it, but don't execute on it. It's a pretty normal mechanism you have these days to prohibit things like executing things from the stack. But we can use it in this case too, because if we just declare our x86 code to be in a NoExecute region, it means that once we are now changing the position counter to go to x86, the CPU will say, oh, sorry, no, you cannot execute that region because it's not executable, and will generate a fault. And that fault we can then again handle, and instead of buffing out, we can just go and call into our QEMU code, which can then go and create a virtual x86 CPU where it plugs all of those registers that we had into x86 registers to basically convert from one calling ABI into the other calling ABI. One nice thing to keep in mind is that not every ABI also has the same semantics. So on ARM, you can have a lot of parameters passed in registers, whereas on x86 with the Windows ABI, you're basically limited to four registers where you can pass parameters, and everything beyond that goes on the stack. So the same code also needs to then take care of those specialties where you basically have, parameters and registers on one side and then in the stack on the other side. So once you have that, you now have your virtual code running. Your QEMU can just execute code inside that virtual machine. It can share data with the outside because data structures look the same. It can execute x86 code until it does not want to run x86 code, right? What happens if you want to print something to the screen? The print function is, again, an ARM function. So what we do is, on any time we see the execution environment fetch an instruction from the outside, from an ARM code point, from something that's not governed inside that x86 region, we again buff out and say, sorry, this is not executable, and marshal everything back again. So we can then just call a normal ARM function from there. Which means we can now just have ARM code calling x86 code, calling ARM code, calling x86 code, calling ARM code. You get the point, right? It stacks as much as you like. It basically is completely nestable. And we emulate instruction set architectures on a cross-function boundary. So it's one address space. You have no idea. You don't get really good hints on whether some instructions are supposed to be x86 or ARM, but you can actually emulate the whole thing thanks to NoExecute. Does this work? That's a picture of me standing next to an AMD Seattle system. That's an ARM server that has an NVIDIA GPU plugged in and displays Graf using the graphical output of that NVIDIA GPU on a screen. Something that looks pretty obvious to x86 people, but it's a miracle on ARM. So why did we even go with QEMU, with QEMU's core called TCG? So there are a couple of reasons why TCG is what was the right choice for this project. One really important one is its C code. All of UEFI is basically written in C. It's not readable C, but it's still C. Which means if you take something like an interpreter written in C++ or written in Ruby or written in whatever other language you choose, that's much harder to integrate than code that is already written in C. It's reasonably well isolated. So I might be biased because I have basically worked on TCG for the last 10 years. So I roughly know what that code does, but I find it reasonably well isolated. It was very easy to take the TCG code from QEMU, take it out, put it into an EDK2 module, a UEFI module, and just run it inside there. There were basically no issues in just copying the code over. The biggest issue, however, was the GPL. So because we're running on the same address space, I really did not want to go through any legal questioning on whether running GPL code in there is then considered derived work. So one thing that was really, really important is that the code is LGPL'd and not GPL'd, which means that project actually is using an older copy of TCG because recently we got a lot of QEMU things creeping into TCG, which then again pull in GPL dependencies, which basically convert the code into GPL code. So this is running on a roughly 5 to 10-year-old version of TCG, which is good enough because back then x86-64 looked almost the same for normal user space applications. And that one was a really big issue. We wanted to have something that supports x86-64. So you find a lot of emulators out there that emulate 32-bit x86 code. There used to be lots of projects that did similar things with VGA BIOS back in the day on Spark machines, on Power machines, on any other, even inside Xorg, you have an emulator that emulates 32-bit instruction sets to run the VGA BIOS for your graphical applications. People have done this over and over again, but only on 32-bit binaries and never on 64-bit and never including all the, like basically plugging in the same driver core as your native modules. Right. So that's why we use TCG. But since you're totally excited about having support for running option ROMs on your ARM server now, how do you actually use that? The easiest way, because you usually don't have an ARM server at home, is to go to that web page. That's the package. So this is basically, this package contains all of the sources of that QEMU module for EDK2. And it contains a README which describes how to build an OVMF binary or AAVMF or whatever you want to call it, a UEFI binary for a virtual machine with that extension included. So the reason it's so split up is that using that same method, if you just echo the include files into a different package down here, you can actually make any random ARM board work with this. If you have a macchiato bin, just build it in the macchiato bin descriptions. If you have I don't know, what else is there? Some Huawei servers have their sources public. So if you have a public board, or even if you have your own private system that you have EDK2 sources for, all you need to do is include these modules and merge this EDK2 tree because it contains 3 commits to basically teach the NoExecute traps into the EDK2 core. Do you believe me it works? So the demo is pretty easy. The demo is an ARM system that has an E1000 card plugged into it, which has an x86 EFI option ROM. And if it works, we have network. If it doesn't work, well, we don't get network, right? So if you just run your EDK2 binary without the emulation, this is just vanilla, normal EDK2 running in QEMU, obviously, because we're KVM foam. So this is just running an EDK2 binary. You will see that, well, it didn't detect any network, right? So even if you do ipconfig ifconfig-l, you will see it doesn't show you any interfaces. If you do PCIe, you will, however, see that there is a network controller, an E1000 network controller. So yes, we do have the network adapter passed in, but we just don't see it as, we cannot execute, we cannot execute the option ROM yet. If we then take a binary that has the patches included, you will see we boot from network, load grub from network, load files via grub from the network, and display a full menu that is actually stored on a TFTP server that gets accessed by the network driver that is all x86 code. You have lots of time left, right? I figured if I have lots of time left, I could talk about 2 other things without slides. So other things that came up while we were discussing what this whole emulation thing should be was EBC. Who of you heard of EBC? Well, there's at least 10 hands. That's good. EBC is something that Intel invented back in the day to have compatibility of option ROMs between 32-bit x86 and 64-bit x86 and Titanium. So it's the only ISA I know of, or pseudo ISA, it's bytecodes, that has a variable size of long. So size of is a function. Yes. The idea was that you can basically take the same ROM and have exactly all those integration pieces, even on a 32-bit system or 64-bit system, depending on which one you're using. We don't really care about that part anymore. I mean, 32-bit systems are not very widely used with UEFI these days. And all the downsides you have, with the emulation, you also do have with EBC. So EBC wouldn't get you any performance gains. EBC wouldn't get you any better standardization on things. Every time you have problems with, say, cache coherency or anything else, you would have the same issues with with EBC as well, but you have more downsides. So lots of modern EFI cores don't even include an EBC interpreter anymore. So you could, for example, put an EBC piece of code onto your option ROM, but then you plug that card into an x86 server and it doesn't run anymore. It's not really what card vendors want to do. So you can as well just compile either native code, which still works, or just forget the whole idea, which I would prefer. Cache coherency is the other one. So one of the differences between ARM and one of the major differences between ARM and x86 is its cache coherency guarantees. So on x86, you basically almost always guarantees coherent caches. On ARM, you almost never guarantee coherent caches, which is only an issue if you're running with multiple CPUs or if your devices are not cache coherent. However, SBSA, which is the server-based standard architecture for ARM, declares that your PCI Express complex has to be cache coherent with the CPU. So you do know that every time your driver tries to access or tries to DMA anything with the PCI card, these pieces at least are cache coherent. So the only thing that could not be cache coherent would be another core, and firmware really usually just only runs on a single core. So it's not an issue. With that, any questions? Wait a second, I got a microphone here. There you go.
In order to translate the function calls between the two architectures, don't you need to know the signature of the function in order to?
No. If you just, you would need to know the signature if we were using floating point. We don't use any floating point at all anywhere in UEFI, I think even by definition. So because of that, everything really only gets passed in registers or on the stack in individual 64-bit chunks, which then again means they're identical. The ABIs happen to be identical between 32-bit and between 64-bit x86 and 64-bit ARM. That things like for example, one thing that could be different, right, is I have only a 32-bit value in my register, or my argument is only 32 bits wide. And on one ABI, I declare that the caller needs to clear the upper 32-bit, and on the other one, I declare that the callee needs to clear the upper 32-bit. But all of these pieces happen to be the same across the two. I think it's on purpose. I think they try to be compatible.
Thank you.
That's one back there.
I'm still confused as how when you do the marshalling, how many parameters you know to copy.
12. 14.
But what happens if you have var args, for example?
Say again?
Var args?
Oh, var args are the same as normal parameters. They're just on the stack.
Right.
So we just basically copy, I think, 14 or so it was.
So you just have a hard-coded limit. You always copy all the registers and then some depth of the stack.
Yes,
Okay.
because we always know we're pretty deep into the call stack, so we know that we're not going to overrun the stack anywhere.
Can I ask a question? I would love to see you doing this in user space, so you can link different architected libraries and use mmap instead of changing page table entries.
Repeat that.
I would love to be able to see you doing this as a user space process, so that different libraries can, written for different architectures, can be linked together, and then you'd use mmap instead of page table entries.
That might work. You will have the cache coherency problem. But, well, the argument, so it works as long as you don't use floating point because they're incompatible, and it works as long as you don't use SMP. But if you limit yourself to a single-threaded process that happens to link something to it, that might work. I'm just not quite sure I see the big benefit of it. But it should, in that, if you constrain your problem space enough, it might work.
Just for fun.
So one question about the trapping mechanism. Does EDK2 or any of the apps, do they actually use NoExecute, especially for security? Because usually it's used for security, and you don't want things to execute when you jump to those addresses. So you could imagine that people would put x86 shellcode onto your ARM system, and it would work thanks to QEMU. So what do you think?
So you saw the GitHub page that I linked to. The whole project was a collaboration between Art from Linaro and me. Art did the EFI part, the backend plumbing, and I did the emulation parts. The whole reason I even got the idea of using NoExecute for it was a presentation by Art at the one Linaro Connect half a year ago, where he presented that now UEFI can use NoExecute because he implemented NoExecute support in UEFI. So obviously that same person kind of grasps how NoExecute works and should work. So that trap handler does not trap and then immediately goes to QEMU. There's a whole framework that basically says, oh, if I trapped in that PC range, then I can register for a callback that then gets jumped to. So the way this works is that you jump into an x86 location, you get into the NoExecute handler. The NoExecute handler goes through a list of different registered handlers, and if one of them says, this region I would really rather like to handle myself, then it just swaps the PC to that handler and returns the signal, basically.
Thank you.
So when you said that you have to mark the function boundary, so when you said you have to mark the function boundary, I'm just curious if there's anything like, for example, I don't know, so inside UEFI, if you have to handle exceptions, will that break your function boundary?
The question is who handles exceptions where. So you do have different interrupt priorities, which basically exceptions can fall into, but I don't, in theory, there's nothing keeping you from nesting exceptions in this case, I think. So you could even have an interrupt handler fully implemented in x86 code that then has a NoExecute handler that immediately gets jumped to after you arrive in the interrupt handler. I think they're all stackable. That's good enough. Not fully stackable, but stackable enough for this use case. Yeah, should work.
Thank you.
You mentioned earlier that you're using 5-year-old code because of LGPL compliance. Is there an effort to purge the GPL portions out of upstream code so we can modernize it and keep it up to date?
There's no reason to. I mean, I'm pretty sure it was a reasonably conscious decision even to have GPL code in there that creeps into every single piece. So I think that's on purpose. I'm not saying I'm sympathizing with the decision, but that was a decision that was made, and that's very, very hard to revert, and I don't think it makes sense to revert either. It's just something to keep in mind for heavy GPL advocates, that sometimes the GPL can actually hurt reach of a project.
it's the same topic. I didn't get the point right now because there's QEMU, and I just read it up, so it's GPL version 2. Is it correct? So actually Wikipedia says it.
So the way licenses work is that a project usually isn't licensed by a project inherits its license by the pieces it's composed of.
Yeah.
So a particular QEMU binary is basically the overall most compatible license between all the source file you compile to generate that binary.
The worst of all.
Right, and the lowest common denominator, or not lowest, but the most viral common denominator between all the different licenses in the QEMU code base is the GPLv2. It's actually GPLv2 only. But if you don't compile the pieces of code that don't have GPLv2 in the header, then that basically gets accounted as the license that is written in the header. And all of the emulation code used to, at least, be LGPL'd.
But I also read up this TCG stuff, and when you say, so, well, you take old portions of code there, I read up that if you want to support new either host processes or emulated processes, then you need to touch that code. So actually, you forked away at some point in time, and so you have one main fork and the other one, and so how do you support new processes? Either way, host and target.
You don't have to. So the beauty of option ROMs is that they need to be compatible throughout eternity. And you want to be able to plug a PCI Express card into a 10-year-old PC. So that option ROM needs to be compatible to ancient CPUs, so you don't need all the new features. So in this particular case, it doesn't matter. I do agree that I don't like the whole part of the licensing piece, but I would have liked even less the discussions that I would raise with OEMs or silicon vendors that suddenly would include GPL code in their firmware, and then what if suddenly somebody randomly just comes in and says, "Woo, you're violating the GPL here. I want to see the source code of everything."
But all this TCG stuff is only used for these option ROMs, not for other stuff.
The TCG part is only used for running x86 code, and the only x86 code you would be running is an option ROM. There's no point in running the Linux kernel using the emulator on UEFI. So you don't really run binaries. You run the drivers, and the drivers really just means option ROMs.
Okay, thank you.
So this emulated code is running every time you access the device or only at boot time?
It's running every time you access the device on boot time. The emulated code, so that was trying to explain in a 2-minute short version with how the UEFI flow works. So once Linux comes in, Linux has Linux is a UEFI binary, but Linux itself really isn't. The Linux EFI stub is. So the Linux EFI stub is a small binary part of Linux. Well, it's not binary part, it's a source part, but it's a part that gets compiled as a binary, as a PE binary, as an EFI compatible binary, that really just all it does is it fetches everything from EFI it needs to know and then throws it away. So all these boot time services that you see, and this is what drivers really do usually, all these boot time service drivers, they just get removed. Yes, you could run into problems if an option ROM installs a runtime service, which then again would mean it installs an x86 driver into something that gets executed while you're running Linux. But on Linux, we don't support any runtime services that get installed by drivers today. So we don't really care.
Sorry, another question.
It says stop back there. Sorry. What? Thank you.
Unfortunately, well, I wasn't going to.